Hey class, even though we didn't lecture, I wanted to make a video. I thought it would help to make a video on deriving the equations of motion for a spring mass damper system. So let's get to it. So we pretend we've got a wall here that's perfectly rigid and there's no gravity, there's no air, no friction from that, and we have a mass with a mass m, and we've got a spring that connects it to the wall. And that spring is a perfectly linear spring, and so if we displace a mass an amount x, then the force that the spring pulls it back with increases by a factor of k times x, or by an amount k times x. So if you imagine that the mass is initially at some place where the spring isn't pulling on it anymore, it's just, at its rest length. The spring is at the distance, the length that it wants to be at. We start measuring x from that point. Then if we make the mass displace a certain amount x, then the spring is going to pull it back with a force of k times x. Okay. And then we've got a damper here that doesn't care how far away the mass is. It just cares how fast it's moving. So if the damper is being extended, the damper is going to try to pull back on the mass. So if the mass is traveling at a speed of x dot, that's the velocity, the time rate of change of x dot is dx dt. Let's call it a velocity v. If it's moving with a velocity v to the right, then the damper is going to be pulling it back with a force that is just c times the velocity v. Okay? We'll see that on our free body diagram. Okay? Let's look at it in our free body diagram. So we imagine, this is how I like to draw my free body diagrams. I say, all right, let's say that my mass was displaced a certain amount x. What direction is the spring going to be pulling back on it? The spring is going to be pulling on it to the left. If I'm going to displace a certain positive x amount, then the spring is going to be pulling it back towards the wall. So that's the direction I'm going to draw my arrow, kx. I do the same sort of process with the damper. I say, all right, well, if the mass were moving in the positive x direction with a speed x dot, then what direction is the damper going to be pushing on the mass? The damper is going to be pushing to the left to resist that motion. And the force is going to be c times x dot. All right. So here's our complete free body diagram. These are all the forces that are acting. We don't have any gravity. We don't have any friction due to other things. I also don't draw like mx double dot. If you've seen that on free body diagrams before, I don't agree with that. That's not a real force. That's not an applied force. I draw only the externally applied forces in my free body diagram. Okay, so let's continue on this. I'm just going to invoke Newton's second law. The sum of the forces in the horizontal direction is equal to, well, this kx, that force is acting in the negative x direction, so I'm going to go ahead and give it a negative sign here. And this force, cx dot, is acting in the negative direction because left is negative according to this coordinate that I've chosen. So minus cx dot is equal to mass times acceleration, right? The sum of the forces is on a system is equal to the mass times the acceleration of the center of mass of the system. That's what Newton's second law says. And in this case, the acceleration is x double dot. It's the second time derivative of my position variable x. So mx double dot. So if we want to rearrange this, we're just going to add kx and cx dot to both sides. We've got mx double dot plus cx dot plus kx is equal to 0. All right, there's our equation of motion for the system. Next step is to solve this equation of motion, and this is a linear second order differential equation. Let's analyze that. So we said it's a linear. That just means that the derivatives don't appear, or the variable itself, x dot, x double dot, those don't appear with like squared or inside of a sine function. It's just the variable or the derivative itself lying out there in the equation, not multiplied times another one of them or something like that. It's only multiplied by constants. That's All right, it's also second order. We say second order because the highest derivative that we have is x double dot. It's the second time derivative of that variable. This is an ordinary differential equation as opposed to a partial differential equation because we only have one variable that we're taking the derivative with respect to. We could also, I think it's also homogeneous, they say. If you might remember this from math, I think that's how it's spelled. I think that means that we've got a 0 on the right-hand side. It's not being forced in any way. Linear second order ordinary differential equation. Okay. So let's go ahead and start solving it. And the way we solve it, there are general solutions for linear second order differential equations. But we're going to solve it from scratch, kind of from scratch, right? We're going to assume a form of the solution. We're going to guess that it is a certain kind of function, and we're going to solve for the different parameters that the function has to have in order for that to truly be a solution. So we're going to guess, in this case, that our function is, we're going to guess a solution x of time is some function e to the rt. We're going to guess that that's the right form. And we're going to, t is just time, e is a constant e, Euler's the exponential, e, and r, then the root of the natural logarithm e. So r is some variable that we haven't determined yet. We imagine that there is some constant for which this will be a solution, but we don't know what the value of r is. It turns out we're going to see that r is going to depend on our quantities m, c, and k somehow in our equation. Something else we know is that if we have one solution and we have another solution, the differential equation, let's say that x1, let's say we find out that that e to the r1, that's a particular value. We figured out what r is going to be, and it's this value r1. I don't know what it is, but it is some definite value. We figured out that this does solve the equation. If that solves the equation, then we know that we can multiply by some other constant times our solution, and this is also going to be a solution. That's something we know from the linearity. I'm not going to go into the math behind that, but it's pretty simple to show that if this is a solution, the e to the r1t, then you can multiply it by any constant, and it's also going to be a solution. Let's say we have a second solution. You can have multiple solutions to the differential equation. And that's just some constant times e to a second r times t. This is another value of r that turns out to make this be a solution. And this is a constant that we can multiply it by. That's no problem. It turns out that another solution, we could get yet another solution, x3, is just the sum of x1 of t plus x2 of t. That's another thing that happens because of linearity. Not only can we multiply a given solution by a constant and get another valid solution, we can add solutions together in order to get a complete solution. Turns out we're only going to need 2. We won't get into the math of that, but I just wanted to give you a little refresher. And so we're going to have to solve for what those constants might be in order to satisfy certain initial conditions. Because we're trying to describe a system. We're going to have an initial value problem. We're going to have, well, let's go ahead and write this now. We're not going to solve this part yet, but we're going to see that x at time t is equal to 0. At time t is equal to 0. We're going to want that to be some displaced a certain amount initially. At time 0, we want the x coordinate to be some value. I'm going to not give it a number. I'm going to keep it general in terms of a variable, x naught, to mean x at time t equals 0. This is some number that if I'm trying to solve for the motion of this mass as a function of time, I need to know where it's starting from in order to solve it. And that's what that number is going to be. And I've got this x dot at time t is equal to 0. The initial velocity, that's going to be some number as well. I'm not going to put in a particular number in there. I'm going to leave it as a variable. We're going to end up solving this equation here, this equation of motion, for these initial conditions. And we're going to get some solution out of that. But right now, let's just try to figure out if this is a valid solution, all right? All right, let's check this out. The way we do it is we plug this into our equation of motion here. By plug in, I mean wherever it says x, I mean I put in e to the rt. Wherever it says x dot, I put in the time derivative of x. So I'm going to have to calculate that. X dot of t is the time derivative of e to the rt. Well, let's do that. So we remember, hopefully, that the time derivative of e to the t is just e to the t, right? We know that. That's from basic calculus. You might also remember the chain rule. And the chain rule says that if you've got some function of some other function of t, and you want to take the derivative of that, well, then you take the derivative of the outer function with respect to the inner function, and you multiply that by the derivative of the inner function with respect to time. And you kind of think of it like, oh, well, that crosses those things out, right? So that's how you take the derivative of that function with respect to t. How are we going to apply that here? Well, in this case, our outer function, f, is equal to e to the g, and our g is equal to r times t. So df dg, well, that's just derivative of e to the g with respect to g. That's going to be just e to the g. And the derivative of g with respect to time, okay, well, that's the derivative of r times t with respect to t. Well, we know that the derivative of a constant times the variable that we're differentiating with respect to is just that constant, okay? So dg dt is equal to just r. All right, so we know that by the chain rule, the derivative of f with respect to time then is going to be the product of these two things. So that's going to be the derivative that we're after here, our d dt of this whole thing, well, let's go ahead and write it up here, is equal to e to the g times r, but g is just r times t, so this is r e to the rt. All right, that's it looks way more complicated, right? Once you kind of memorize how to use the chain rule and it becomes very quick, then it's not nearly as complicated, but if you have to think about it in these terms, here are the steps. You take a look at, oh, well, you recognize I've got some outer function and some inner function. I know the derivative of e to the something, right? Let's say it's t, I know that, and I know the derivative of this part, and so I'm going to think of this as a two functions. One is inside the other. Then I can apply the chain rule. But it becomes second nature. All right, so r e to the rt. That's the chain rule. All right, so that was a digression. Let's go back and take this derivative, right? This is r e to the rt, x double dot. We're also going to need, because we have x double dot here. If we want to plug things in, we need to calculate what x double dot is. Well, forget the constant for a second. We can differentiate this again. That's just going to pull out a factor of r. So this is going to become r squared times e to the rt, right? Because we don't have to worry about the constant until afterwards. We can take the derivative of the important thing and then multiply that by the constant later. That's one way to think about it. All right, so we've got the three derivatives that we needed, and let's plug them in here. All right, so if we plug them in, we get m times r squared e to the rt plus cx dot c times r e to the rt plus k times x is e to the rt, plus k e to the rt, and that all still has to equal 0. If this is a solution, then when we plug it in, it still has to equal 0. What does that mean for us? Well, we can factor out this e to the rt, and we get this mr squared plus cr plus k, right? We've got everything is multiplied by e to the rt, so we can pull that out and separate it into two pieces, e to the rt. Okay. These are equivalent, right? And what this is telling us is that either one or both of these has to be 0 in order for this to solve our problem. Can e to the rt ever be 0? at time t equals 0, e to the rt is 1, right? Because e to the 0 is 1. Maybe if r is negative and we go really, really long in terms of time, this can be 0. But we're not interested in, just a particular. We don't want this. We need this to be true for all time. We want this to represent our solution to the problem, right? We want this to tell us how the mass is going to move. So we can't count on it being a particular value of time. We need this whole thing total to be 0 for all time. All right? So we can't count on a particular value of time. So e to the rt, if it's only 0 for a particular value of time, particular r, it's not going to be able to describe our situation. We need something that's going to describe our situation. We kind of get to choose which one of these is equal to 0. Yes, you could say this is a solution if you make t infinity and r negative, right? That's one way of solving this. But another way of solving is by making sure that this is equal to 0. So that's the route we're going to take. We're interested in this way of solving it. We want that to be 0. And that puts a condition on what r can be. It says, if e to the rt, you want e to the rt to be a solution? All right, well, in order for that to be true, then this has to be true. So we can find out what r needs to be in order to make that happen. Use the quadratic formula. Quadratic formula, forget for a second that this variable is called c. I'm just going to write out the standard quadratic formula, right? The two roots, r1 and r2. Right? We're going to get two roots from the quadratic formula because there's that plus or minus in there. It's negative b plus or minus the square root of b squared minus 4ac all over 2a, right? So this thing here, m, that is our a in this case. This c here, well, in the quadratic formula, that's really b, right? And k here, k, this in the quadratic formula, that's what we're going to call c in the quadratic formula. I know it's a little bit confusing. I used that same letter there. Oh well, this is the way that we know how to write the quadratic formula. So let's substitute everything in. Negative b, so that's really negative c plus or minus the square root of, well, that's really c squared minus 4 times m times c is k in this case, okay, all over 2 times a, which is m. Okay. So in order for e to the rt to be a solution to our differential equation, this is a requirement. R can be one of these two values. Negative c plus the square root of this thing over 2m, or r can be negative c minus the square root of this over 2m. Those are two values it can be. All right, and we talked about it before. We know that the full solution then to our problem, if we've got two solutions, we know one solution has r1, the other solution has r2. We can apply constants on both of them. Then the whole solution is going to be a linear combination of them. So our real solution, our full solution, x of t, is some constant. We don't know what it is yet. We still don't know what this one is yet. Times e to the r1 times t. At this point, we know what r1 is. It's negative c plus the square root of this over 2m. Plus c2 e to the r2t, where r2 is the minus version of that. We don't know what c2 is yet. So we still don't have a complete solution to our problem. We're going to end up using these knobs, c1 and c2, in order to satisfy our initial conditions. All right, before we get to that, before we start solving for particular initial conditions, let's analyze the behavior here. What does this e to the rt look like? Well, you remember that if e is positive, or r is positive, then e to the rt, where r is a positive number, here's t, here's e to the rt with r is positive and real, a real number, like 1, then we get some exponential like that. It's going to blow up. Okay, if r is a negative number, r is negative, real, then we're going to get some solution that looks like this. You can plot it on your calculator if you don't believe me. That's how those r functions behave. If r is a complex number, well, let's start with just pure imaginary first. Okay? Let's say r is imaginary. Well, for that we're going to have to remember Euler's formula. Euler's formula says that, let's say, e to the I times, we'll give theta. It can be, we can use any variable here, but let's use a variable that's not one of the ones that we're already using, is equal to cosine theta plus I sine of theta. Okay? So in our case, e to the I times r is equal to cosine of, well, e to the I RT. Well, r is an imaginary number. Let's say it's, let's say r is equal to I times, let's give a number to it, p. Okay, I times p, or p is, let's say positive. It means positive real. Okay, so this becomes e to the I pt plus cosine is equal to cosine of pt plus I sine of pt. Okay. So it turns out that when r is an imaginary number, this one in particular, then e to the ir is equal to the e to the ipt, which is equal to this thing here. So it turns out that our solution, at least the real part of our solution, is going to be oscillatory at this point. Okay. So the real part is going to look like this. It's going to be a cosine function, etc. And it all depends on the value of r. Let's go ahead and, yeah, we'll continue. The next thing is if r was a complex number, right? R, I didn't choose my variables ahead of time. P, yeah, here we go. Actually, we'll call this Q. I think that'll be good for us. We're going to make this a Q. Okay. Where Q is a real. And IQ is what makes R complex. I being the square root of -1. Okay, so let's now think about what if R is complex. Okay, so R is equal to P, a positive or a real number. It could be positive or negative, but it's real. It's not imaginary. Plus I times Q. I is the square root of -1. Q is also a real number, but I times Q becomes imaginary, and so P plus IQ becomes a complex number. All right. In that case, if we apply Euler's formula, then this is what we get. We would see that e to the r, which in this case is p plus iq times t. Well, that's equal to e to the p times t plus iqt. If you remember something about sums when they're in the exponent from the exponential function, sums become, you can break them apart into two separate exponential functions multiplied by each other. That's just a property of the exponentials. It's kind of like saying, all right, 2 squared, well, if you multiply that by 2, well, that's like 2 to the 1, right? Times 2 squared, well, that becomes 2 to the 3, right? If I multiply by 2 again, well, that becomes 2 squared, right? Well, that's now 2 to the 4. You're adding the exponents, not multiplying them together. That's a bad example. Let's stick with 1, 2, and then 3. All right? We add the exponents. It's just a sanity check there. So likewise, we can take a sum, which is really 2 plus 1, and we can break it up into the two pieces. That's what we've done here. We've taken this sum, we've broken it up into two pieces and multiplied by each other. All right, but e to the pt, with p being a real number, it can be either like this kind of exponential or that kind of exponential, right? Positive or negative, exploding or decaying. And then the IQT is this complex thing. At least the real part of it is this. Cosine wave, right? And when you multiply them together, it means that you point-wise you say this times that, and this times wherever it is at the same time, etc. And so what you end up with is, let's say it's a decaying exponential. Let's say that p is a negative real number. Then you end up with this, so let's say p is negative real, and q is, let's just say positive. It really doesn't matter, actually. Real. Then you end up with, here's our t, and here is our, e to the p plus iq times t. We're going to end up with this guy here. But that's kind of controlling the magnitude. The sine function, or the cosine function, it never gets bigger than 1 on its own. But when you multiply it by e times p to the t, well, then it's going to get up as high as up to here. And but it can never get higher than this, right? So it's basically scaled by whatever the exponential function is. So it's not constant, but it's like, it's a non-constant amplitude. Turns out the amplitude starts out really big, and then it decays. And so the cosine function starts out really high, okay? And as it goes, it can't get any higher than this line, etc. All right, so it's actually kind of bounded by the top, on the top and the bottom. So you got this decaying sinusoid. So those are the different forms that our solution can take, at least qualitatively, in terms of depending on what r is. And r is controlled by this expression here. Can we get these different cases? Yeah, we can get pretty much all of them, except for this one. All right, so we know that m, k, and c are always going to be positive. That's a given. To be physical, things have to have positive mass. A spring that produced a force that was in the same direction as the displacement, that would be nice if it existed. That would allow us to have perpetual motion machines, right? If the spring were to push this, if you displaced it, if it pushed it away even further, then this thing is just going to accelerate. It adds energy, so that can't be possible. And C, likewise, if we get this thing moving, then the force pushes it even faster. That's adding energy. Dampers don't do that, okay? So we're dealing with C, M, and K are all positive real numbers. So what can this be? All right. Well, we know that negative c, how could this thing possibly become a positive real? Let's start out with that. Well, that would happen if negative c plus whatever this thing is, if this thing was greater than c, if this turned out to be a number that was positive and greater than c, then we would end up with this thing being positive, right? Let's see that that can't happen, right? We need, in order for this to happen, we would need to have negative c plus the square root of c squared minus 4mk. This thing would have to be a positive number that's greater than c. Okay, so we would have to have this is greater than or equal to c in order for this to be, on the whole, a positive number, right? I suppose we could also end up with a negative number here and subtract it, but you'll see that that can't happen either. Okay, so we really only need to consider this. All right, if that is the case, well, let's square both sides. Okay, c squared minus 4mk is greater than or equal to c squared. We can subtract c squared from both sides, okay? That means that negative 4mk is greater than or equal to 0. This is nonsense. M is positive, K is positive. -4 times a positive number cannot be greater than 0. So we've just shown that that's not possible. This whole thing can never be positive. We're never going to have a positive, exploding sort of exponential. Let's see if this thing can be real. Okay? How can we make this thing be real and negative? Yeah, we want this thing to be real and negative now. How is that going to happen? In order to be real and negative, well, then we'd have to have negative c. Well, let's see. Real and negative, we'd have to have negative c, either plus this thing or minus this thing, has to be less than 0. Yeah. All right, negative c. Let's start with negative c plus this thing. Plus square root of c squared minus 4mk. This has to be less than or equal to 0. All right. Well, this means square root of c squared minus 4mk is less than or equal to negative c. Let's square both sides. Then we have c squared minus 4mk is less than or equal to c squared. Well, sure, that's easy. That just makes sure, all we need to do is make sure that 4mk is, it's always going to be, less than or equal to 0. But there's a possibility actually that this becomes imaginary. Okay? So let's consider how this whole thing could be, how this portion could become imaginary. Right? So here we've shown that yes, we're going to sometimes have a negative part of this thing, but let's see how this and that's going to give us a decaying exponential kind of solution. But it's possible that this term goes to be an imaginary number, right? If this inside were negative, we could have that sinusoidal sort of solution going on, or the decaying sinusoid. So let's see how that can happen. We're saying that if this here is imaginary, that means that the inside of it has to be negative, okay? So c squared minus 4mk is less than or equal to 0. If that's true, then that is negative. Inside is negative. That means this whole thing is imaginary. We have some complex thing